All right, let's take a look at the warm-up. So, folks should be away, ready to get started here. We have a warm-up, solve the differential equation subject to x of 0 equals 0. What is my first step in solving this differential equation? Divide by 2 I hear. Let's divide that thing by 2. I get to a form that looks like this, dx dt plus x equals 2. A standard form here. Once it's in a standard form, I'm able to find my integrating factor. My integrating factor should be e raised to the integral of what? 1 dt. So I get e to the t is my integrating factor. Multiply through the whole thing by my integrating factor, I get this. I then recognize that this whole expression on the left is really just the derivative of the dependent variable times the integrating factor. And that should be equal to 2e to the t. And then I want to do that mental check, right? Okay, the derivative of the product is the derivative of the first thing. That's my dx dt times the second e to the t plus the first thing x times the derivative of the second thing e to the t. So we just kind of mentally go through that product rule, because if you made some sort of mistake along the way, that will catch that little mistake. Any questions so far? All right, what's my next step? Integrate. Integrate both sides with respect to t. Integrate with respect to t. On the left, I get x e to the t. On the right-hand side, I get 2e to the t plus some constant. Make sure you add it right then. And then lastly, I'm going to take that whole equation and multiply it by e to the negative t. Or divide it by e to the t, whichever is your preference. I will get x is equal to 2 plus some constant e to the negative t. Any questions so far here? All right, that thing is subject to x of 0 equals 0. I get 0 is equal to 2 plus c1 times e to the 0, which is 1. Looks like c1 is equal to negative 2. And my final solution would be 2 minus 2e to the negative t. There's my solution. Any questions about the solution? Did anybody do it differently? Everybody did that same way. Nobody did anything different. All right. My first class, I had one person do it differently. What did they do? They did this. They divided through by 2, but after that they went dx dt is equal to 2 minus x. They then divided by the right-hand side to get this, because this equation is separable. Separated the variables, integrate both sides. Over here, you got to be careful. Do you get natural log of 2 minus x? Negative natural log of 2 minus x is equal to t plus some constant multiplied by a negative equals negative t plus some different constant, or minus c1, either way. Exponential of both sides gives me 2 minus x equals e to the negative t plus c2, which I can rewrite as some new constant, e to the negative t. And then I just solve it for x, add x to this side, subtract off this guy. I get that. Plug in my initial condition, sure enough, I'll get that thing. So you can do it by either technique. This one you can solve by the linear technique because it is first order linear, but it's also separable. You can do both. Any questions? Yep. Absolutely. Remember, what we're finding here is some function, and the whole idea is that's a solution because it should satisfy the differential equation. So if I want to check my work, I'm going to calculate the derivative of this result. The derivative result is going to be 0 plus 2e to the negative t, right? That negative comes down. So that's my x prime, right? It's 2e to the negative t. And x we said was 2 minus 2e to the negative t. I'm just going to plug that into my differential equation, which was 2x prime plus 2x equals 4, there we go, and see if it works. So 2 times x prime, that's 2e to the negative t, plus 2 times x, 2 minus 2e to the negative x, that should be t, right? That should be t. And that's supposed to equal 4, right? Question mark, right? What do we get here? 4e to the negative t plus 4 minus 4e to the negative t equals 4. Looks good, right? That cancels with that. 4 equals 4. Pretty happy I got the right solution. Good question. Other questions? Any questions in general? All right. All right, we're going to cover section 1.5 today, exact equations. Exact equations. All right, so this is one of those sections that it's challenging to write. See, when you write a textbook, you have to write things that you have to write. In class, I can say things, I can give you kind of the down and dirty approach, really focus on the process. But when you write, you have to be pretty formal in how you approach things, right? So I find this section a little hard to read, right? There's formal notation that can make it a little challenging. But what you really need to do is go through that formal notation, struggle with it, come to class, get the overview, go back to that formal notation, because it makes you a better reader of the textbook, right? It really is a valuable tool, not only for math classes, but especially your engineering classes, they get more mathy, right? So we're going to go through the kind of the down and dirty exact equations. What is an exact equation? An exact differential equation is one that can be written in either of these forms, right? So your textbook will look at this form. That's the partial of capital F with respect to x. The partial of capital F with respect to y times y prime, or y prime is just dy dx. That's the form the book uses, but I do want to show this other form as well, right? Because you'll see that in certain physics courses and certain engineering courses, kind of more of a differential form. Now we do have a relationship between these little differentials and the derivative, and we've said that we have the real analysis and the background to kind of be able to treat those things algebraically. And so really, if you rewrote this guy as dy dx and then multiply through the whole equation by dx, you basically get the second equation. Okay? Kind of a little heuristic approach, but they're both saying the same thing basically. Question? No subscript, that's a comma, right? So my function f is a function of two variables x and y. Are you looking at this guy? Right, f of x comma y, right? So in general, f is this guy right here. It is some function of x's and y's. So it's a function of two variables. So what does it mean? Derivative. Well, how does f change as you change x or change y? So now we have partial derivatives in here. Okay. So on the left-hand equation, I'm being explicit about the variables, whereas on the right-hand side, the right equation, that's still the same function, capital F. I'm just not explicitly stating that it's a function of two variables. Good question. Other questions? Okay. So if our differential equation can be written in this form, then it's an exact differential equation. And oh, by the way, the solution is whatever that function is equals c. There is the solution of the differential equation. Yay! All right, it's right there. But of course, when we're given the differential equation, we're not given it in this kind of pretty form. We're given something like this. Consider y cubed plus 3xy squared times y prime equals 0. Is this differential equation exact? Well, it kind of looks like one of those forms. You know, if this thing was the f sub x here, the partial with respect to x, and this thing over here was f sub y, then yeah, it would be exact, right? But we would need that to be true. What we would need, I'll scroll this guy up here, it would be exact if there exists some function, capital F, where that was true, where the partial of f was y cubed, the partial with respect to x is y cubed, and the partial of y is equal to 3xy squared. So if I can find that capital F, or that F exists, then yes, it is exact. Okay? That's the first kind of question, right? Does that thing exist? And if it does exist, what's the next question? Anybody? Yep. Well, what is the constant? We'll need that at some point if we have an initial condition. But more importantly, what is F, right? Like if it exists, what is it? Right? That we got to find it next. So the first step is saying, does it actually exist? And the next step is, if it exists, what is it? Right? Because once we find that, then we can just write out a solution. There it is. Okay. Right. The big idea is this. Now we got three big questions, maybe, right? One is kind of like the setup question. Why? Oops, that shouldn't be equals 0. But why is that thing even a solution? Why is this, exact equations thing work? But then from a process standpoint, how can we tell if it's exact? And then if it's exact, how do we find capital F? Right? So I don't want to start looking for capital F if it doesn't exist, right? That is a waste of my time. Okay? So first we check for existence, and then we'll actually find what that is. But first, why does this stuff even work? Sorry, people are still copying stuff down here. Now the book will use kind of one explanation using certain notation. I'm going to use a little bit different notation to make the same justification. So you can compare the two approaches. All right. If y was some function of one variable, right? Calc 1. I always start with Calc 1, right? Well, then we have this guy. This guy is the differential. Right? And that is the definition of the differential for one variable. dy is the derivative times dx. Like, what's the change in y? Well, you can take the slope, the instantaneous rate of change, times a little change in x, dx, and you should get a little change in y, dy. Okay? It's the idea of the differential. And that's basically what it's saying, is how is y changing as I change x? What is the change in y? And we have this relationship. What about if we have more than one variable, though? What if z is now a function of x and y? Well, it's more complicated now because, well, how does z change as we change x or as we change y? So we have maybe a more complicated definition of the differential. This is the definition of the differential for functions of variables. You should have seen that in Calc 3 if you've taken Calc 3 already. Okay? Any questions about that so far? Okay. And lastly, we have a little question. What if z equal to f of xy, what if that thing was just equal to a constant? What does it mean for z? F of xy is equal to some constant. That means if I know x equals 2, y equals 4, I'm fine. Right? X equals 3, y equals whatever, I'm fine. Geometrically, what is that guy? Just a plane, right? A flat plane. So how does the height of that plane change as I change x and y? Doesn't, right? So what is dz equal to if my function is a constant? 0, right? So if that guy is a constant, then dz is equal to 0. But dz is equal to this thing, so what do we get? We get the partial of f with respect to x dx plus the partial of f with respect to y dy is equal to 0. Right? What we basically set up is this thing. If that function equals constant, then that equation is true. Okay? I really want to use it the other way around because that right-hand side is the form of our exact equation. I want to say if that's the exact equation, then f equals c is the function. That tells me it's a solution. But there's one little limitation for me going both directions with this if-then statement. It's the existence of f. Right? To go the other way around, I'd say if this equation is true, if there exists an f for that equation to be true, then I can say f equals c is true and it's a solution. Okay? So that differential discussion just connects these two ideas. That's where it comes from. You take your definition of a differential, consider a constant function, and then boom, there comes your exact equation. Okay? That's the relationship between the two. But how can we be sure if there exists an f? Here's kind of our existence idea. Recall from Calc 3. If f is a nice function, it's well defined, it's a regular nice old function, then the mixed partials of that function should be equal. Right? You take the partial with x and the partial with y. It doesn't matter which order you do that, you should get the same result. So the mixed partials should be equal. So the idea is that if we can check to see if those mixed partials are equal, if they're equal, they must be coming from some f. That f must exist. That's the idea here. Okay? So what does that mean? Well, here's our equation again. And I'm really hoping that that's f sub x. And I'm really hoping that this stuff over here is f sub y. Okay, well, if that's f sub x, I'm going to use that to calculate f sub x sub y. To do that, I'm going to take the partial with respect to y of that guy y cubed. So I'm assuming that guy is the partial with respect to x. What do I get there? I get 3y squared. Okay. If this other piece is f sub y, the partial with respect to y, I can use that to calculate f sub y sub x. What's that guy going to be? Partial of this thing with respect to x, which is 3y squared. They are equal. Okay? And then I say because, right, fxy is equal to fyx, right? The differential equation is exact. That's my test. If those mixed partials are equal, I may proceed with this process. That tells me that there does exist some function f. Huh? Questions so far? Yep. Well, my form in general is this, right? My general form for these exact differential equations is this. And so I'm just trying to get these two pieces. Okay. Good question. Other questions? Remember, if you got a question, someone else got the same question. All right. Yep. Fy needs to be the coefficient of y prime, right? Or in that other form, like this, right? We're matching this differential, right? So f sub x has to be the coefficient of the dx. This has to be the coefficient of the dy. Good question. Any other questions? Okay. All right. Now, that's not what the book writes. The book writes this. Let's rename that first thing little f, and let's rename the second piece g, and then we'll calculate partial of f with y and g sub x, because then little f sub y is really capital F sub x sub y, and g sub x is really capital F sub y sub x. Okay? Why do they do that? Why do they throw in little f and little g and just give you more? Right? Right? I am working with f sub x before I know it exists. So it's really bad notation, it's a little kind of cheating. But I'd rather do that than introduce a new lowercase f and lowercase g, right? The idea is we're hoping. We are hoping that that is true, and we are hoping that this is true. And if the mixed partials are equal, then it is true. Does that make sense? Yeah. Usually, ugly notation in textbooks is there because of that kind of reason. because to write it cleaner is cheating. And if I cheat in class, well, you can't really prove it, but if I cheat in the textbook, then I can prove it. So, all right. Anyway. All right. Exact or not exact? Clicker question. Let's see if we can use this idea now. All right. Exact or not exact? I'll even help here. I'll write the two general forms, right? It's f sub x, f sub y, y prime equals 0, or f sub x dx, f sub y, dy equals 0. Once again, those come from that multivariable differential. All right, what do we got for the first one? I'm hoping for 120. All right. All right, pretty split here, 68 versus 43. Let's take a look here. All right, what's the idea? The idea is I am hoping this guy is my f sub x. I'm hoping this guy is my f sub y. And now we need to calculate the mixed partials. F sub x sub y is going to be the partial of this thing with respect to y. I'll get 2x plus 2y. My experience that one of the harder pieces of this is just if you haven't seen partials or you're rusty on your partials, calculating the partials. You're just treating the other variable like it's constant. Sometimes it even helps to write in 2, right? Write in some constant value in there. Give you a sense of what's going on. What about the next one? I need to calculate f sub y sub x. That's the partial of this thing with respect to x. That'll give me 2x plus 2y. Sure enough, they're the same. That one is a exact. Questions about the first one? Number 2. I'm seeing a lot of good discussion. If you have questions, feel free to talk to your neighbor, check what they got. All right, what do we say, 115? Very mixed, 50-50 almost. Let's take a look at it. What is the partial of this thing with respect to y? Well, that first whole term is just x stuff, right? So I'm treating like that like it's a constant, like it's all just some number 3. What's the derivative of 3 with respect to y? 0. Okay? The derivative of some number with respect to y is just 0. The derivative of some number times y is whatever that constant is. Right? But that whole first piece is 0. Then what's the derivative of y with respect to y? That's 1. So that piece is 1. And then I take this piece, the partial of that thing with respect to x, that's also going to be 1. So this one is also exact. So you thought it was going to be B because I just did an A. Came back with A and A, right? Next one's got to be B, though, right? All right, let's take a look here. See what we got. All right, mostly B. Let's verify here. If I take the partial of this thing with respect to y, that's a constant, this is a constant. It's really like doing this, right, which would give me just the constant. In this case, it would be x e to the x. Over here, the partial of this thing with respect to x. That's really the same thing as doing this. If y is a constant, this is a constant times e to the x. Well, that derivative is constant times e to the x. Same thing here. Y e to the x. Okay, so this one is not exact. Any questions so far? All right, I'm just going to do the last one here. I'm going to take that last one. I'm just going to rewrite this left-hand side as dy dx, negative y times x. I'm going to multiply through by x and dx. I'll get x dy, negative y dx. I'm going to add this piece to the other side. I get y dx plus x dy equals 0. Where I'm hoping that this thing is my f sub x and this thing is my f sub y. To check that, I'll calculate f sub x sub y, which is 1. And I'll take the partial of this thing with respect to x. I will also get 1. That one is exact also. So that one's exact. Is that one separable? That one is separable, right? I would divide by y and multiply by dx instead of dividing by x, but it is separable. Is it linear? What variable am I checking for linearity? I'm checking the y. I have the derivative of y raised to the first power, and I have y raised to the first power. That one is linear as well. Okay? So I could use any of those techniques on this differential equation. Any questions? All right. Now we know how to check to make sure that it's exact. Because once again, I don't want to waste my time doing it through a process if it's not even going to be exact. If it's not even possible to be correct with that process. But now that we know we can check it, what's the full process of actually finding out what f is? Okay. All right. I have it kind of sketched out on the left there. Here's my example. The first step was to check to make sure it's exact. So once again, I'm hoping that this is my f sub x piece, and I'm hoping this is my f sub y. And I'm going to do my check. I'll take the partial of the first piece with respect to y. I will get 1. I will take the partial of the second piece with respect to x. I will also get 1. Yes, it is exact. Okay. It is exact. So that means I'm not cheating with my notation anymore. There really is this capital F that makes that true. That tells me that it really is an f where the partial is equal to 2x plus y. And there really is that same f where the partial of y is equal to x plus 6y. Those things are true. I like to write those true statements down at the top of my solution process. That's really what I'm working with. That's the given information here. Now, how do I find f? Well, I'm going to start by integrating this one with respect to x. Sort of. I'm going to do a partial integration with respect to x. So like you have partial derivatives, you have partial integration. And it's the same idea. You just treat the other variable like it's a constant. So if I do a partial integration, the result will be f. And that will be the integral of 2x plus y. And if I integrate the first piece, I'll get x squared. Treating y like it's a constant, if I integrate that constant with respect to x, I would get that constant times x. And just like regular integration with differentiation, I can check my work. I should be able to take the derivative of that and get back to the integrand, right? But this time I'm taking the partial derivative and hoping to get back to the integrand. Okay? So what's the partial derivative of this? That would be 2x plus y. Looks like I'm doing it good, right? But what's the partial derivative of that? Same thing, right? I forgot to add my constant. But what's the partial derivative of this? That's also still just 2x plus y. So in this case, I don't have to add a constant, I have to add more. This could be not only a constant, but could be any function of y. That weird little notation is psi. Kind of a sloppy psi, but. Okay, so when I do this integration, I have to have this general function over here. That is any function of y. Because if I put any function of y there, and I were to take the partial derivative with respect to x, it would disappear. Okay? It would be 0. Any questions so far? Okay, remember the goal here is to find my solution. My solution looks like this. It's trying to find that function f. Great, I almost found it. This is what I have so far. I've almost found my solution. But I got to figure out what that psi function is now, right? The way I'm going to find out what that psi function is, I'm going to take what I have for f so far, and I am going to calculate f sub y. Okay? And in my steps, I wrote it differently. I wrote take the partial of the f plus the psi piece that you just calculated. I am not grabbing this yet. I am calculating the partial of my f here. Okay? When I calculate the partial of that thing with respect to y, I get 0 plus x plus psi prime. That is me calculating the partial of this thing. Arrow. Now I wrote psi prime there, but I'm only taking a partial derivative with respect to y. Shouldn't I get the partial psi with respect to y? How come I just write the derivative? Because it's only a function of y. Right? Psi is not a function of x and y, just y. That's going to be okay? All right, cool. There it is. Partial of f with respect to y. X plus psi prime. But I also know the partial of f with respect to y is the other piece. So now I'm going to set those two things equal to each other and solve for my missing psi. Okay? So now I take this guy, right? X plus psi prime, and that guy, and they're supposed to be the same. Okay? I'm going to subtract x from both sides. I get psi prime equals 6y. I subtract that x from both sides, it has to. If you solve that for psi prime, and you have x's on the right hand side, you have done something wrong. Right? Because we said that psi has to just be a function of y. Okay? So now I know what psi prime is. I integrate both sides with respect to y. That means psi must be 3y squared plus some constant. That was the missing piece for my solution. Now I know that psi is just 3y squared. Do I have to put my constant c1 there? Why not? Right. If I put it there, I would just subtract it to the other side. And I would take my two constants and give them a new name, new constant, right? And that is my solution process. Okay? So I wrote those steps down the left. What am I going to do? Check the criteria. I'm going to integrate f sub x with respect to x. That's going to generate my first attempt at f plus an extra constant of y. Then I'm going to calculate f sub y from the f I had, and then I'm going to set the two fy's equal to each other and solve this side and throw it my solution. Those are my steps. You need to write down more steps. Right? You got to write that down in your own words. Whether that makes sense to you. Not formally, but whatever is going to trigger you to get all the way through that problem. Okay? Any questions so far? Okay. Before I turn it over to you to try one with that process, I do have to do this. This is an alternative approach. It tends to be easier. I can't justify it all the way. I don't know if it will work in every circumstance. I haven't found a counterexample yet. So it seems to be pretty robust. You won't find it in a textbook, but every semester a student asks me if it works. I say, I think it does, but I'm not sure. So I'm just going to show you what it is, right? We have f sub x here. We have f sub y here. Somebody always asks, can I just integrate f of x with respect to x and then add that to integrating f of y with respect to y? I say, well, it doesn't work because some of the terms will be repeated and you don't want both versions of them. And then they say, well, can I just take out the duplicates? I say, yeah, I guess that kind of works, right? So what does that mean? So you minus the duplicates. So I integrate this thing with respect to x. I get x squared plus y times x. I integrate this thing with respect to y. I get xy plus 3y squared. These two are repeated. Get rid of one. It's redundant. X squared plus y times x plus 3y squared equals 0. Okay. I hate even bringing that up in class. I'm never doing that other way again. Forget that way, right? I'm doing this thing. Okay? The other way is important because it's a more formal process, and you will have to use that process on other styles of equations in different courses. It's the process that's important. Okay? So I encourage you to use that process. There is also another reason, which we'll get to when we encounter it in a little bit. Okay? That's kind of like the, the cheater approach. Let's just call it what it is, right? All right. Anyway, practice problem. These tend to be long problems. I have 18 people who have solved it already. That seems amazing. Let's check all E's. Almost all E's. What do they know? It's not exact. First thing we do, we check to see if this guy is exact. I take Partial of the first piece with respect to y, I get negative 3y squared. I take the partial of the second piece with respect to x, I get 2x minus 3y. This is not exact. That is the first thing you always have to do for exact. Check to see if it's exact. Otherwise, you waste all that time in the process. Check it first. Okay? Now, this ties into that alternative example. You're using the alternative solution approach. You integrate one, you integrate the other, you put them together. There's no repeated terms. That happens sometimes, and that's okay sometimes. But you will not know that that is an incorrect solution. That everything looks good. Using the formal process, you're going to find out the sine of y is equal to some x's and y stuff. That's going to be a giant red flag because you cannot proceed anymore. You must have missed something. Okay? So you can't finish that process if it doesn't actually work. You can do the other approach, get something that looks right, but is absolutely not right. Okay? So if you're going to do that alternative method, make sure 100% that you are checking those partials to see if it is exact. Okay. So, all right. Now the real problem. All right. I always say that, but then sure enough, in some class I've done that, and this one's not exact either. So I better check myself. Okay. Proceed. Well, I had other typos in this. Let me just change my options here. These should all be zeros. Okay, let's talk through what I got so far here. Okay. We did the check to make sure it was exact. It was exact. Then I take this piece, the f sub x piece, and I integrate it with respect to x. And this is what I get when I integrate it with respect to x. Any questions about that step? Partial integration with respect to x. That's my first expression for f. F looks something like that. I don't know what the psi is yet, but that's my function f. I take that function, this one right here, and I take the derivative of it with respect to y, the partial derivative with respect to y, to get this piece. Okay. Those zeros are because the partial of x squared with respect to y is 0. The partial of negative 4x with respect to y is 0. Okay. But from the problem statement, I also know that this guy is equal to f sub y. So I said those two pieces equal to each other, and I solve for psi. Here's the other big misstep. F is equal to all this stuff, right? I've added in my psi piece. That's what F is. That's not the solution, though. The solution is f of xy equals constant. This is the solution over here. Okay? If you write this down, that is incorrect. You don't write f equals all that junk. Your solution is the sentence, the equation f equals c. Okay? All right, from there I got to find my constant, so I use my initial condition. That condition says when x equals negative 1, y is equal to 2. So that means I have 5 times 2 times negative 1, negative 10. I have negative 1 squared. I have positive 4 here. I have y squared. So 2 squared is 4, positive 8, minus 2 equals c. So it looks like c is equal to negative 9, negative 5, positive 3, positive 1. Okay? So that would be the specific solution. Now I want to find out what y of 0 is. Okay, well I'll plug in x equals 0 everywhere. Looks like I'm going to get 0 plus 0 minus 0 plus 2y squared minus y equals 1. How do I find y now? I subtract 1 over, I use quadratic formula. Turns out I'll find out that y is equal to 1 and negative 1/2. So the answer was D here. But 2 y values? Is that okay? What does that tell me about my solution here? Is my solution a function? No, I can't find an explicit solution. I have to leave it in this implicit form, and that's okay. Susan Turner probably goes like that or something. It fails the vertical line test, that's okay. Now, what I'd like to explore for Thursday, I'm going to start to discuss with this, is you can check to see if this all makes sense. You can use contour plot in Mathematica to plot this solution. Okay? And then you can see if these values make sense when you're thinking of x equals 0. You could do the slope field, reform the original equation so you can make a slope field and plot that contour plot on it. That's what I'll start class with next time. Also, real quick, for the weeks upcoming, here's a little roadmap. Thursday, we're going to start 1.6. Tuesday, 1.7 is the application section. So we'll be taking the application and reviewing chapter 1 through that application. We'll also have a chapter 1 quiz on Tuesday. Now we can return to you the following Tuesday. Then when we're comfortable, finish up 1.7 and review, and the exam that following Thursday. That maps out kind of the next 2 weeks after this week. All right.